Hello, my name is William Leese and I'm a second year master's student in the Radio Navigation Lab here at UT, which is affiliated with the Wireless Networking and Communications Group. I've been researching signal processing for newly developed low-cost radar chipsets, which are fueling the adoption of radar by the automotive and robotics industries. Such chipsets are available from several manufacturers for the millimeter wave frequencies, and they achieve impressively low SWaP-C, meaning they have low size, weight, power, and cost. They've already seen widespread use in the automotive industry for blind spot detection and adaptive cruise control, but their short range currently prevents their deployment in long range applications. Our research aims to increase the range of low SWaP-C radar with extended measurement intervals and specialized radar signal processing, which is applied to the raw baseband radar signals. With extended range, low SWaP-C radar will drive innovation in long-range applications like urban air mobility and urban air logistics. Urban air mobility and logistics refer to the worldwide efforts to offer low-cost air transportation to people and products using autonomous, vertical takeoff and land vehicles. A low-cost radar solution will be instrumental in realizing this concept since the autonomous aircraft will need to be able to sense and avoid obstacles in their airspace. Frequency modulated continuous wave, or FMCW architecture, is popular for low-cost radar because it provides high range resolution and requires relatively low digital sampling rates. It operates by emitting so-called chirp signals, which increase in frequency over time. If the signal-to-noise ratio is high, then only one chirp may be necessary. However, longer range implies lower signal-to-noise ratio, which necessitates collecting multiple chirps over a longer measurement interval. After some initial processing, the chirps form a range-time matrix, where a target signal is centered in a particular range bin at each chirp. Even though the target signal is present in each chirp, it is not strong enough to be detected. If the target is stationary, it's easy to combine multiple chirps into a single high SNR signal. This is achieved by coherent integration, where the desired signal's complex measurements are simply summed to form the high SNR signal. If, however, the target is not stationary, then the measurements from consecutive chirps will not have consistent phase. This phase drift can cause the signal to effectively cancel itself in a complex sum. Phase drift is almost always present in practice because the phase of an FMCW measurement is sensitive to wavelength level target movements. So for millimeter wave radar, the problem is unavoidable. Another problem related to target motion is range bin migration, where the target moves enough to occupy different range bins in consecutive chirps. This causes the signal to spread out in a simple complex sum, which makes it undetectable in noise. To solve these problems, we start by deriving motion models for radar targets, which describe how targets are able to move relative to the radar. Here, natural constraints apply, like the thrust and weight of a target vehicle. These models make it possible to define a maximum likelihood estimator, which finds the most likely target position given a set of FMCW chirps. Although this estimator achieves the best accuracy, it's not practical to implement because it's very computationally inefficient. To mitigate that issue, we developed suboptimal estimators which are more efficient and still achieve very good performance. These suboptimal algorithms leverage additional signal processing to correct phase drift and range bin migration, which allows the radar to achieve a high SNR signal and detect moving targets at long range. These algorithms were validated in simulation and tested in a small-scale experiment. The results show that our techniques will help make long-range radar available at much lower SWaP-C, which will support innovation in urban air mobility, urban air logistics, and a variety of other robotics and surveillance applications.